finish up section 15.5, but before we do that, I want to give an opportunity for questions from stuff. So I think we should be able to do up to 138, but anything in there is fair game questions. Luke looked like you were getting ready for something.
Yeah, 124. I'm really confused what to do with the E is there.
Okay. No problem. We can take a look at that. So we have 2e to the 2x plus 5e to the x minus 3 equals 0. So to me, this looks like a quadratic. So I'm just going to make a little substitution to really illustrate the quadraticness of it. So we'll just say that e to the x is equal to y. So we have a quadratic equation. We can solve that quadratic equation a couple of different ways. Factoring or the quadratic formula seem the most appropriate. Maybe you can look at that and tell that it factors right away. It does, but the factoring process can be kind of tedious, especially when the leading coefficient isn't 1. I would probably just use the quadratic formula here because I know that's going to work. I mean, it does. It'd be like what? 2x minus 3 times x. I'm sorry, 2x minus 1 plus or times x plus 3, I think is what you do, but you know, we're not all math teachers where we can factor something like this in our head. All right, so we have 5 squared is 25 minus a negative 24, so that's 49. The square root of 49 is 7. So negative 5 minus 7 divided by 4 is negative 3. And negative 5 plus 7 divided by 4 is 1/2. But remember, we want to solve for x. So we'll go ahead and take those solutions for y and substitute back in our e to the x. So I just have 2 little dinky exponential equations to solve. So to solve an exponential equation, we need to use a logarithm. The logarithm I would use in this case is log base e, also known as the natural log. Now, I know that I can't take the logarithm of a negative number, so this solution doesn't give me anything in the exponential, which is fine. So I'm just going to get the one answer for the natural log of 1/2. So a negative 0.693-ish. Does that feel okay, Luke? So whether that exponent base is e or 2 or 7 or 13, it doesn't really change the process a whole lot. John, what do you got?
How do we get a negative answer from Euler's number, which is positive, 1/2?
Well, e to the negative, well, let's just, e to the negative 6.93 or whatever is 0.5, right? So like the negative makes a reciprocal,
It's a fraction.
right? And then the 0.693 is like a radical, so it's also making it smaller.
Yeah.
So you have like 1 over, it ends up being close to 2 with that 0.69 power on it. And obviously the exponential can't give you a negative. That's why it just gives us no solution for that part. Because I can't take a positive number and raise it to a power and get a negative. Whatever the power you pick is, you can't get a negative. So is that okay? Jacob.
Just like a random question, can you put E in on your calculator, the value for it?
Yeah, so if you just do like the E and press enter, it'll spit out the value. Or if you wanted to use the other one over here with the exponent built in, you just put a 1 in the exponent, press enter, spits out the value. Is that what's up?
You can't do that now. Solve these ones.
What do you mean can't do that?
You can't just. Oh wait, no. Never mind. Sorry. That was dumb.
No, it's okay. You could do, if you wanted, when we did the log base E, instead of using the natural log, you could do, you know, this and you'll get the same thing. So you could use the number or whatever in the base of the logarithm, and that's fine.
Yeah.
But the natural log is built into our calculator. I mean, I'm going to just use that because it's less buttons and I'm efficient. Sure. Others? Anybody else? Jacob.
You do number 26 or 126.
126? Sure. So we got 400 over 1 plus 95e to the negative 0.6x equals 500. All right. So I noticed that the variable location, it's in the exponent of a number in the denominator. So first thing I would do is try to get that out of the denominator. So I would just cross multiply. Cool there. We'll divide both sides by the 500. I'm going to reduce as I go. Good there. We'll subtract 1 from both sides. I made some common denominators and stuff to do that subtraction. And then I'll divide both sides by 95. Really, I'm going to think about multiplying by the reciprocal, just so I can do that in my head. What's that going to be? 425 or 475, I think. I'm going to check that real quick. I guess it's pointless if I'm going to do it in my head to bother to check it, but yeah, good. Okay. And then if I go and I take the natural log of both sides, what's going to happen? Can I take the log of a negative? Nope. So this is no solution. Yeah, and that should come as not too big of a surprise considering we have a, Which one did you pick? 126. Oh, well, Jacob, that's the reason why is I wrote down the wrong number here. This number is supposed to be 150. So, oops. Let's see if that makes a difference. Oops, that would be 40 over 15, though. So yeah, that's going to make a big difference, huh? I subtract 1, that's going to be 25 over 15. And then it's calculator time for me, my friends. 1 over 57 positive sorry about that, Jacob. It's a good thing we checked though, huh? To make sure. And then I'll just divide both sides by the negative 0.06. I'm going to write it as multiplying by the reciprocal though. Just so if I go back and look at that, it's super clear to me whether that dividing by negative 0.6 was inside the logarithm or outside the logarithm. Here it's super clear that it's outside the logarithm. But it's very easy if you write that as division for it to be kind of unclear to the reader yourself later on if you go back and look. So I get about 6.74. Yeah, no problem. I think even if I had done it for the wrong number, it would have been pretty clear as to like what, you got what you needed to out of like, how do I solve this thing, right? It's probably the process more than anything else. But let's shoot for writing down the right problem. You know what I mean? Seems like a reasonable expectation to have. Okay. Anybody else? Okie dokies. Let's get the ball rolling then here, folks. We're going to finish up section 15.5. So in section 15.5, we're going to be doing, we're talking about financial mathematics. Woof! Money! Okay. When we talk about mathematics in the realm of finance, kind of the first place we want to start is with interest. So when I say interest, what do I mean? Do I mean like something that's super fascinating? That's what an interest is? No, not when we're talking about finance. What is interest? It's like some... Sure, so it's like some money that you earn on a investment, right? Or it could be like the fee that you're charged for a loan, right? That's basically what we're talking about. So there's a couple of different types of interest. The first type is simple interest. In simple interest, you're earning interest only on your initial investment. So our simple interest formula, FV is equal to PV times 1 plus RN over 100, where FV is like the future value. So if you make some investment, that's the value of that investment in the future. PV is the present value. That's going to be like the amount of money you initially invested. R is the interest rate expressed as a percentage. And then N is the length of your investment, so like the number of years. So let's look at an example here right quick. So you invest $2,000 at a 6% interest rate. How much money do you have in the account after 3 years? Well, start with that. Which one of these parameters am I solving for in this question? Yeah, so you're talking about how much money is in the account in the future. So we're looking for the future value. Cool. All right, so what goes in for PV? The 2,000. Great. And how about for R? 6. And for N? 3. So you type that all into your calculator, you get $2,360. So how much interest did you earn? Yeah, because we just take the future value and minus the present value. So you made $360. Cool. Now, in the banking sector, do we use simple interest? Almost never. Okay? The reason being that it doesn't really make sense to me that in year 2, I'd have $2,120 in my account. Why isn't my interest payment based on what's currently in my bank account rather than just the 200 or the 2,000 that I started with? So when we calculate interest that way, that's always based on the current account value. This is called, oh, I need a name here, compound interest. And the way we calculate compound interest is with this formula. So PV or FV is equal to PV times 1 plus R over 100K to the NK. Now the FV, PV, R, and N are the same values, like they're the same parameters as before, so I'm not going to write those again. Is everybody okay with that? The K, though, is a new parameter, so let's describe what that is. That's going to be like the number of compounds per year. So I'm guessing that most of you guys have a bank account, or a lot of us have a bank account, probably at least a savings account. Have you ever looked at your bank statements? Okay, how often do you get interest charged or earned on your account? Is it every statement? Typically, a bank's going to pay you interest like 4 times during the course of the year. So that's kind of typical on a savings account, is the interest is compounded quarterly. But when we talk about the number of compounds per year, that value is always going to be kind of hidden in words. It's never going to be like expressed as a number inside the problem. It'll be like, hidden in words. Right? So like quarterly would mean 4 or something. And we'll talk about some of the vocab here in a second as to that. But let's do a quick example first. Say if you invest $2,000 at 6% interest, or at 6% interest rate compounded annually, how much money do you have in the account after 3 years? And then how much did you gain in interest? What word in here is super important in choosing between the simple interest and the compound interest formula? Yeah. So as soon as I hear that word compounded, I know that I'm going to be using this new formula. Okay. And this sounds like exactly the same situation as the previous one, except it's compounded now instead of simple, right? So we're still looking for FV. PV is still 2,000. R is still 6. N is still 3. But what is the K in this situation? 1. Why is it 1? Yeah, so that word annually is our Q for the K. Cool with that, my peeps? Okay. So let's take a look at that. Oops. So there we earn $2,382.03. So what was how much, let's see, which one was better? The simple interest or the compound interest? Yeah, the compound interest was better. By how much? About 22 bucks. Not real impressive, right? But let's see what happens if instead of just doing this for 3 years, what if we do this for like 30 years, like a really long time? So here's my simple interest for 30 years. Get 5,600 bones. All right, cool. If I do my compound interest for 30 years, oops, wrong spot. I make, whoa, almost 6,000 bucks more. That's a big difference, right? What's going on there? Why is that difference so big? Yeah, so you're right on. Come on now. So my simple interest is like a linear function, right? You're just 120 bucks every year. That's it. Our compound interest is exponential. So if you look early on, not a whole lot of difference between the two, right? But we go far enough out in the future and whoa, buddy, there's a big difference. Cool. Let's start talking about the effect of K. So just some basic vocab here. We saw that annual implies that K is 1. What would semi-annual mean? K is 2. How about quarterly? Tells us K is 4. Monthly? K is 12. Weekly? 52. Okay. Daily? K is 365. Okay. So let's take that same situation we've been working with and look at what happens when K is 1, 2, 4, 12, 52, and 365. Okay. So here's K equals 1. I'm going to change that to K equals 2. What do you think? Is this going to have little effect, medium effect, big effect? What do you think? Well, it's certainly going to have an effect. Way to couch that in a way that you take no risk at all. All right, let's see. About $6 difference. Not a whole lot. Well, what if we go from 2 to 4? Do you think it's going to be a bigger effect from 1 to 2 or less effect? More effect. Let's see. About $3 more. I'd say that's less. What if we go from 4 to 12? This time it's a 3-fold change, right? It's 3 times as much as the previous. Here, that's got to be a lot, right? $2. It's getting less. Well, what if we do 52? That's like 4 times as much, over 4 times as much as the previous one. That's got to make a big difference. 80 cents. Well, shoot, Mr. Kulik, let's go to 365. That's like, you know, what, 7 times as much? That's like a huge jump. That's got to be 20 cents. So, it seems that as the K is getting bigger and bigger and bigger, yes, we are making more money, but the amount the amount of total increase you're getting gets a little bit less as K is getting bigger and bigger and bigger, right, Sergio? Sure. So, what is the most times you could have, you know, like the most number of compounds we could have in a year? You do more than hours. You do more than seconds. What's that? Yeah, so we would say that would be continuously, which would be basically every instant. Okay. Now, I can't exactly go and plug infinity in for K in the previous formula. That's not going to do much for me. So we're going to have to think a little bit harder about what's going on here to make this thing work. So I think I'll probably end up having to do something clever, but we're going to start with our compound interest formula. And the first thing I'm going to do is I'm going to just rewrite this in a clever way. So I'm going to rewrite this as 100K over R. I'm going to write the exponent as 100K over R times N R over K. Nope, over 100, excuse me. Yeah. So why is it okay to do that? If I multiply those two fractions together, what do I get? Now I get NK, which is the same thing I had in the exponent before. So it's definitely okay that I did this, right? Everybody buy that? Now the question of why did you want to do it that way, that's a different question. Let's get to that in a minute. It'll become obvious here in a moment. I'm going to now make a substitution, and I'm going to rewrite 100K over X as, or 100K over R as X. So if 100K over R is X, what is R over 100K? 1 over X. And then that's an X. Maybe I'll make it a bracket. And I'm going to write that as an exponent of an exponent. Anybody recognize this fella right here? We talked about it this chapter, but it was before spring break. So if you don't remember, that's probably why. Let me go back and show you. Where'd you go? There we are. That is E, right? The limit as x goes to infinity of 1 plus 1 over x to the x is just E. That's what I'm going to use. This is why I did that, rewrote it in that particular way and made that particular substitution. So we know that k is going to infinity, right? That's the situation we're in. So 100K over R, well, that definitely goes to infinity then. And since that's X, we know X is going to infinity then. Everybody agree? So I can then take that yellow piece and replace it with E. And now that I've removed K as a parameter, I don't have any place to substitute the infinity into. So this is my new formula for continuously compounding interest. That's so neat, Mr. Kulik. I know, man. Where did that go? There's what I'm looking for. Once again, all these parameters are the same parameters we've seen in the previous formula, so I'm not going to rewrite what all the abbreviations are. Everybody's cool with that? If you're not, say something, and we can write them, but it's usually the case. Okay. Next example, Jack invests $800 into a savings account with 5% annual interest rate compounded continuously. How long will it take for Jack to have $500 in interest? We have now 3 equations to pick from. What word or words in this are going to tell me which equation I need to use? Yeah, compounded continuously tells me that I need to use this most recent formula. Okay. And then which of these parameters am I going to be interested in solving for? Was the question asking me to solve for? How long? So n, yes, very good. So that's what we're going to be solving for. Everybody cool? All right, so let's start filling stuff in. Where does the 800 go? That is the present value. Very good. Where does the 5 go? It goes in for R. Yep. And then, well, we still got FV. What's going to go in for FV? Yeah, where'd you get 1,300 from? So that's going to be the present value plus the interest. So that's where John got the 1,300 from. Everybody's cool? Okay. To solve this, what's the first thing I should do? Divide by 800. When I do that, I get 13 over 8. Everybody's okay with me reducing there a little bit? And the exponent can reduce down to just be n over 20. Everybody's cool with me reducing that a little bit? Okay. What's the next step? Yeah, natural log both sides. Dead on. And then multiply by 20. No big deal, right? Looks exactly like the kind of solving we did in the previous chapter. In fact, this is like kind of in the easiest version of those solving problems we saw in the previous section. So I get about 9.7 years or 9.71 years. All right, unrelated example. So here we says you find an account that has a 6.5% annual interest rate compounded monthly. What would be the equivalent interest rate for an account that is compounded annually. Okay, well, it sounds like I'm going to have to do something for monthly compounding and something for compounded annually. Everybody agree with that? So which one of the formulas do I need to be using? What word or words is telling me what to do? Yeah, so I hear compounded and not continuously, so I know that I'm going to be using that standard compound interest formula. So when I write this down, I can see right away that it doesn't seem like I have enough information to solve everything or to fill in all the parameters, right? So I know I'm going to have to do something kind of sneaky or clever here. Maybe it's not entirely apparent to me right now what that's going to be, so let's just kind of fill in what we can and see if some good idea comes to us. All right, so if I look at the monthly situation, what can I fill into the monthly equation? Okay, I can fill in R. Is there anything else? Yeah, K. What's K going to be in this case? Sergio, can you? Oh, yeah. Yeah, just enough to keep it from latching. Thanks, guys. So I'm going to write it like that. Everybody cool? Let's do the same thing for the annually. What can I fill in for the annually? Just the K. And the K in that case is 1. So I'm not going to write the 1s in. I'm just going to write it without the Ks. Is everybody all right with that? All right, let's look at what we got here. So these parts are all the same, right? Everybody agree with that? So if these two exponential equations need to do the same thing, then I know that the bases for those exponentials have to be equal. Everybody good with that idea? If everything else is the same and they have to be doing the same thing. Okay, so to solve for R, what do I need to do? How about I subtract 1 and multiply by 100? That sounds good, right? Yeah. Oops. So 100 times parenthesis, parenthesis. Oops, not yet. 1 plus so when I do that, I get about 6.7%. Now, this process that we've just done turns out to be quite a useful one in a practical standpoint. Why is this, what would we, in finance anyways, what would you potentially use this to do? Well, no good ideas, so I'll just tell you then. We could use this to compare two like investment opportunities to really see which one is better. Because if I ask you what's going to be better, 5.75 compounded weekly or 5.79 compounded monthly, it's maybe not entirely clear which one would be better, right? So how could we check? Doing this. So we actually have a name in finance for this because we do it so often. This is called the annual percentage yield, or APY. And it's basically just the conversion to the equivalent annual interest rate, right? It's exactly what we just did in the previous problem. So what I'm going to do is I'm going to write a formula for this based on the previous work. So I'm going to have 100 times the quantity 1 plus R over 100K to the K minus 1. Right, these are, I just took what I did in my previous work and turned it into a formula. We cool with that? Let's do an example here. So it says, we have, which saving account is the better investment? One that pays 7.8% interest compounded quarterly, or one that pays 7.65% interest compounded weekly? God bless you. All right. So we have these two situations. Anybody want to venture a guess as to which one is going to be the better one before we calculate it and find out for sure? Okay, let's death match here. So I'm just going to take my APY formula that I stated above, and all we need in the formula is R and K, and we have both of those provided, so it's just like a straight up plug and chug situation, which is okay. So I'm just going to take the previous problem and just edit it for our purposes here. All right, so the first one I got, it's equivalent to 8.03% interest. And the second one, put in the 52s for the Ks and change the R to 765. Oops. At 794. Oh boy. So when we say better investment, we want the bigger APY, right? Oh, excuse me. All right. One more financial concept to talk about here. So this last concept is called an annuity. And this is an account into which a sequence of payments are made. And specifically, the kind of annuity we usually are most interested in, and will be in this class, is the ordinary annuity. And this is an annuity where the payments are made at regular intervals for the same amount. So when we talk about an ordinary annuity, what type of situations does this sound like in like the real world? So a loan, for sure, right? If you borrow money, like to buy a car or a house or, open a small business or whatever, you take a loan and you're going to make regular payments at the same time every month. Yep, absolutely. So there's a loan way that we can use this annuity idea. And the other way that nobody thinks of because you're 16 or 17, like a retirement fund, right? Like if you get a job and you're saving for retirement, typically you save kind of the same amount every month or every paycheck or whatever. You just, you chip in 5% or 10% or whatever of your paycheck. So it's like the same amount every month. So there's kind of two different versions of this annuity. So we do like an investment annuity. Which is future value equals R times 1 plus little I to the big N minus 1 over little I. Here we're seeing some new parameters, so let's define these. So R is whatever this regular payment amount is. So like $100 or $200 or 37 cents or whatever it is you're saving every month, or paycheck or whatever. I is just going to be R over 100K. And capital N is going to be lowercase n times K. And we've already defined R, K, and N, so I'm not going to define those again. I should probably be specific. Little r, K, and little n. So let's do an example. So here it says, at the end of each quarter, Sarah makes a $500 payment into an annuity account. If her investment earns 7.88% annual interest compounded quarterly, what will the value of Sarah's annuity be in 20 years? Well, this sure as heck sounds like the investment annuity situation to me. Hopefully that's pretty obvious to you guys. What parameter are we solving for here? The future value. So that value of the account in the future. Okay, so let's start filling things in. What are we filling in for R, capital R? The 500. Good. And then I'm just going to write it this way, and I'm just going to off to the side write down the stuff for I and N, because it gets a little busy if you try to write that all in the same formula, you know. So I was lowercase r, which would be the 7.88 over 100k. What's the k in this case? Quarterly. You know, either place is fine. And then n is nk. And now it's just straight up calculator time. So 500 times. And if you haven't been using the fraction command on the reg, it's time to get comfortable with that fella, because he is going to be your friend here. Because I'm going to use it a whole boatload of times when doing this annuity stuff. Oh, yeah, thank you. And this is a situation where you probably, oh boy, want to practice typing this stuff in to your calculator, because, you know, it is just like what it looks like on your sheet of paper. But if you haven't been using the fraction command on a regular basis. So $95,483.39. Yes.
Is it possible that you make a payment in a time frame different than what the interest is compounded?
Yeah. You have to deal with it a little bit differently, and it's beyond the scope of what we're going to do here. But it has to do with like really the parameters of what. In a loan situation, it's a little bit more clear, because usually the loan companies just they do different. It really depends on the investment, like their rules on how things are going to work. So in the case of you putting it in early, you might get a little bit more interest, ended up paying on that because it's in there for a little bit longer, you know. Or if it's a loan, if you make more than the payment you're supposed to, oftentimes they'll credit that towards the principal rather than the interest. Or sometimes they'll might do something else, or if you're late, it end up paying extra interest, so your loan, you know, goes up, and it just kind of depends on what they're doing. But that's a reasonable question, but it's so specific to like, what are the rules for your specific agreement on how we're going to treat these things, that it kind of becomes beyond the scope of what we're going to do. But it basically deals with like, how are we going to calculate the extra interest earned or penalized by making your payment early or late, or in the case of paying more than you're supposed to, specifically on a loan, how do we treat that monies? All right. The other situation is where we do an annuity as a loan. So this is going to be a little bit, the formula is a little bit different, because if you think about what a loan really is, it's like you have a account with negative money in it, and like you're trying to pay that down to zero rather than like new money coming in. And obviously a loan stops at a fixed number of times, like they don't just keep collecting money from you even after you've paid off your debt. So the formula works a little bit differently. Notice here that instead of it being FV, it's PV. And you could think about PV as present value, but it's really kind of more like the principal value here, like the initial investment or the initial loan amount. But that's really the way you want to think about it, is like the loan amount, like how much you're borrowing. Okay. But all the other parameters are the same as the ones we had mentioned earlier, so I'm not going to redefine them. That's okay? Okay. So Maria buys a new car for $18,500. What are the monthly payments for a 4-year loan if she makes a $2,000 down payment and her annual interest rate is 2.9%? I hear the word loan in here, so I'm going to use the annuity formula for a loan. What are we going to be solving for in this problem? We're looking to solve for the monthly payments. So that's going to be the R is what we're going to be looking to solve for. Cool with that? So let's start filling things in. The PV is 16,000, right? So basically the price minus the down payment. Right. For those of you that familiar, when you go in to buy a car, you usually pay for a little bit of it up front. That's the down payment. And then you borrow the rest of the money that you're short. When getting a loan, oftentimes to the customer, the most important factor is, what's my monthly payment going to be? Right? Like I know I can't buy this whole thing right now, but so I'll get a loan, but I need to still be able to afford whatever the payment is each month. So this question of like, what's the monthly payment is almost always the most interesting one for the customer. All right. So we have this. The lowercase I is the interest rate divided by 100K. What's the K in this case? The K is 12. And then cap N is going to be the N, which is 4, times the K. So to get the R by itself, I'm just going to divide that whole fraction to the other side. That's going to be my equal to R. Again, I'm going to use that fraction command on my calculator. And if you have not been using it, this is the one where like, boy, this makes life so much easier if I'm able to do that. So I have a fraction, and then the denominator of the fraction, I have another fraction. And then in that fraction, I'm going to have a fraction. And then in the denominator of that fraction, I'm going to have another fraction. Who is sick of the fractions here? So when I do that, my monthly payment would be $364.49. So one more question here, and it's the obvious next one. Is what did old Maria here end up paying for the car? What are all the things that Maria paid? How much did this car actually cost her? So we paid the down payment, right? And then we're paying $364.49 once a month for 4 years. Everybody buy that? So $19,495.41. How much of that was interest on our loan? I'm going to take the total cost and subtract off of it the price, right? So I ended up paying about $1,000 in interest. What do you guys think? That's it for the chapter 15. Overall, I think this section is maybe the easiest one, because it's so much just kind of like plug and chug. You know what I mean? So we'll stop here. We got, 10 minutes left or something?